Welcome to the ongoing course of perception algorithms for autonomous systems. So, last week or last lecture actually we have trying to solve one problem, and we wanted to compare extended Kalman filter performance and the pseudo measurement filter performance. So, we solved the same bearing only tracking problem that we selected in last class, and we solved the extended Kalman filter. Also, we told about how the pseudo measurement filter is implemented. Pseudo measurement filter, and we shown the Monte Carlo simulation comparison study between the two filters, how the filter is behaving. So, I would like just to start with that lecture once, since we have not yet completed the full lecture series last week, yesterday. So, in the pseudo measurement filter, what we did, so this is the same, if you remember the old problem, you remember this is a 1D or 2D bearing only angle tracking problem. So, you have your line of sight angle measurement is available up till 20 seconds, and your platform is perturbed with a mean motion plus a delta motion. Delta motion is say white noise, zero mean white Gaussian noise, and mean motion is also marked for xp equal to or xp bar is equal to a time, it is a function of time, a ramp function, yp is a constant. So, that means that two dimensional y axis is keeping constant. You have this is your this thing, your system state, and you have this is your measurement. So, in the pseudo measurement approach, what we did, we won't talk EKF again. So, what we did, we just constructed a pseudo measurement. So, pseudo measurement how we constructed. So, this is actually your actual measurement, line of sight angle measurement or azimuthal angle measurement. So, I did that simply tan of theta, tan of eta divided by yp by x minus xp, then sin eta by cos eta, and we derive a noise free pseudo measurement as zs equal to x1 minus xp into sin eta minus yp cos eta. So, actually what we did, we actually did sin of eta equal to yp divided by x1 minus xp by cos of eta, and then we derive that x1 minus xp sin of eta minus yp cos of eta, basically this is equal to 0. So, this total, the term which is equating to 0, that part actually we have taken a pseudo measurement. So, once we have taken pseudo measurement, then we have to derive its statistics, first order statistics, second order statistics. So, what is the delta component? Do a first order Taylor series linearization. What are your dependent variables? Delta x1 is your one dependent variable, xp is another dependent variable, yp is another dependent variable. So, you have to calculate the deltas with for the zs. So, you have to calculate it accordingly. So, with this now expectation of zs is coming as equal to 0. So, average value is 0, and the variance value is expectation of zs squared divided by expectation of zs. Now, simply it is simple algebra. If you can compute this partial derivatives, it is lengthy, but you can easily calculate the partial derivatives of this whole thing, because eta is also another function of tan inverse yp divided by x1 minus xp. So, if you calculate and this and taking your expectation is anyway 0, first order moment is 0. So, second order moment you can take your expectation of your delta x1 square is equal to say p x x1. So, first diagonal element of your P matrix, expectation of your xp square is equal to say what I have told, what is the value I have denoted is I think delta xp, that is all I have done. So, that means Rx, that is what. So, actually Rx and Ry. So, Rx actually the value. So, it will be equal to say Rx expectation of yp square Ry, and simply calculate it, Once you calculate it, you can find your statistics is somewhat looking like this equation or even this equation also. This will be your equation. So, this equation now is conditioned on measurement theta m, but when you actually I told multiple times, if you remember my pseudo measurement filter flow chart, it has to be estimated with your predicted estimate. So, let me go through the some before. If you see this, so when you have converted measurement error, forget Cartesian and all this thing. So, when you have converted this measurement, so your same flow chart is running. So, you have time update, you calculate your predicted Cartesian, you can remove its pseudo measurement, predicted pseudo measurement whichever you have taken, that z as sine minus cos, that x1 minus xp sine theta minus yp cos eta equal to 0. So, that thing you calculate here. Once you calculate here, then you calculate the r. Already the r you have calculated analytically. Now, calculate it with respect to predicted state, that means time updated state. Once you calculate this, then you run your linear measurement update. Okay. So, with this now, once you calculate, so what is the benefit of this? So, benefit is actually here that I have calculated this pseudo measurement. Once I calculate this pseudo measurement, then my predicted pseudo measurement, my observation matrix becomes like this, sine of eta m into 0. Eta m is anyway is a kind of a measured value. Okay. So, you can use directly a linear Kalman filter to simulate it. So, you can see your measurement matrix is like this, your measurement residual will be this, and this is your this thing, measurement error variance, which you calculate using your prediction, and you run your normal linear Kalman filter equations. So, with this now, when you kind of compare your EKF versus your pseudo measurement, okay, I removed a small thing, just a correction, this won't be particle filter, this is a PMF filter, pseudo measurement filter. When you compare your pseudo measurement filter with your EKF, because I have not simulated EKF, we won't talk about particle filter, we will talk only about EKF and PMF. If you see this, till 100 run, things are kind of identical, both are identical, EKF and PMF are identical. So, it is actually PMF, EKF and pseudo measurement filter. Okay. We are comparing particle filter, we have not simulated, so we won't talk about it. So, with this, if I compare this with 100 Monte Carlo run, then we can see that EKF and pseudo measurement both are kind of tracking to each other, okay, in a kind of almost similar, not very different result. Now, I have increased my run. What does this mean? This is very important to understand. It means that I am changing the, if you are using say MATLAB random number generator or Python or C, whatever you are using, they all use something called pseudo random number generator. And pseudo random number generator is kind of basically some algorithms, that algorithms generate your Gaussian distributed or normal distributed random numbers. So, it starts with something called state, or it starts something called as seed. Okay. And at a particular time, at a particular instance, if your random number generator is good or something, at a particular time this pseudo random number usually repeats itself. Maybe after 1 lakh or 1 million or 2 million Monte Carlo run, it might repeat, the sequence might repeat. Okay. So, this is a numerical property, you can't help it out. So, here we have now at 100th run, when we are taking 1000th run, there is one seed, because this is done, simulation is done in MATLAB, and there is one seed or one state which is making your error too large. So, you see here EKF diverged, but pseudo measurement filter is still converging. So, you have seen this is very important. So, 100 run you have not seen much difference, but when you take 1000 run, you see EKF is off. Now, you have to check the consistency. So, in fact, we simulated this thing almost 1 million run. In the MATLAB code we have different days with different number of seeds, we gave almost 1 million run. With 1 million means 10 lakh Monte Carlo run. In the 10 lakh Monte Carlo run, it has been seen that pseudo measurement and particle filter is staying lock stable, but EKF multiple times it started diverging. That is why when you are studying the convergence of a nonlinear filter, you must use Monte Carlo simulation and plot the either RMS error or the error standard deviation or error variance or something called normalized residual error square, that also can be plotted. So, with this now I go to the next simple thing. Okay. So, how you calculate the Monte Carlo RMS error, that I will tell here. So, in fact, I told in one of my class, but still I will repeat. So, this is your say estimation error, your true state minus your estimated state. Okay. And now I am collecting this value for each and every position error, velocity error, say for every sample, say 1, 2, dot 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 number of sample. Okay. Now, my run 1 with one seed, run 2 with another seed, and write that run n with another seed. With this, I am now capturing all the errors here across the sample, say 20 sample, not more than enough. We are lumping this simulation only for 20 samples. And now, what we are doing? We are taking RMS value of each and every sample, RMS value. So, summation of EI square divided by root n. For each and every sample I am calculating, and that one I am plotting. So, single run, what we have seen in Kalman filter, single run you will have some noise. The more and more Monte Carlo you take, it is doing an averaging over the runs for each and every sample. So, this is smoothing out, you get like this. For nonlinear filter convergent test, Monte Carlo is an integral method. Even if you do a single run test, it may not be proper, you may not be kind of able to kind of predict that this thing is working fine and all. In the next class, I will tell you few more error statistics, that is called Cramer-Rao lower bound, and few others that will tell you what are the necessary criteria when you want to test the convergence of a filter. There will be a separate class for that. Okay. Now, apart from Monte Carlo, there are other things, other elements also there, which can tell you that something that you can do it, okay, with this without plotting the RMS error for so long, so many kind of run, because it will take time. Your system will be overburdened and all, it will take time. So, there are other methods also there. One is called normalized estimation error squared. What is normalized estimation error squared? It is just simply norm of your estimation error. So, actually it is transpose inverse this. This is your actually normalized estimation error squared. So, simply a secondary norm, simple norm function. So, here they plot it the average norm function for a single run. So, single run you can see zigzag, coming up, coming down, coming up, coming down, coming up, coming down. And if you see the true versus estimated plot, tracking okay, but not so great. I am not very happy with this kind of a tracking. Tracking is not so great. This is tracking, but okay, you see the error is too high and very much delayed convergence. Filter is not able to actually jump and properly do truth. This is actually your extended Kalman filter. So, if you plot similarly the normalized innovation error squared, so that will be again equal to norm of zk again. If you plot this over say single run, you got this kind of up and jump, up and jump. So, at least it is 95% level, marking the filter is consistent. So, it is within, say this is your 95% level, 95% of your this chi-square test that I told, the innovation property, as per innovation property. So, with this now filter is kind of consistent. Now, I took a Monte Carlo for this 50 SMC now and plot your RMS position and velocity error. You can see the velocity error is coming down, position error is also okay, but not so great, because we have seen the first blow at 1000 Monte Carlo run. So, this is only 50, but here you can see when I am plotting the normalized estimation error squared. So, that norm of estimation error, you see that most of the time, so most of the time below 95% probability region. So, the innovation is not holding its Gaussian property. If it is holding its Gaussian property, so it will be above 95%. So, that means it will be a chi-square distributed. If it is a chi-square distributed, so taking your alpha equal to 0.05, it has to be above 95% probability region all the time. Here it is dropping, it is dropping. You can see here, it is just kind of 95, it is not reaching the 95% mark. Okay. So, this is kind of, so there is some issue. So, there is some issue. So, issue is even known even if you do not take Monte Carlo run, seeing your innovation error. Since your innovation error squared or norm of innovation, you can clearly see if it is losing its chi-square distribution or not. So, because I told whenever you do not have any truth, how you will check? You check your innovation. Innovation has to be 0 mean, that means there is no measurement bias, plus it has to be chi-square distributed, and chi-square distributed means 95% confidence interval. So, the innovation error squared has to be 95% above your confidence interval, but here it is losing. We can clearly see it in the plot, this plot. It is kind of clearly it is going below the 90%. So, it is not very kind of good, or what I should say, not a good exercise or whatever this thing. Okay. Because quite a lot of time it has covered this 2.5. So, it is going to above 5%. So, it is losing its chi-square test. So, this is the thing. So, if you see even your innovation error score also blowing up from 70, after 17 seconds it is it is jumping like this. So, this is not very good. Okay. So, EKF is inconsistency, it is being proved. So, this is the thing, at least a good example, although there are maths, there are a lot of maths involved in it, but this is a good example to show that why you EKF and what is pseudo measurement filter. Now, there will be a question. What is the question? That question will be, why do not we use EKF then? Why will you use EKF then? Well, you can use EKF. It's not problem is not with EKF or not with pseudo measurement. Problem is actually your system observability. When I am making only one state, and I am because see I do not have any range measurement. Now, if I incorporate the range measurement, my story will be changed, or in fact, if I do a say eta dot measurement, so line of sight angle measurement and line of sight rate measurement, my EKF may work good, because I am giving extra information. This is very important to understand. So, it actually depends on the system observability. What are the measurement I am using and what are the state I am estimating. So, Kalman filter is nothing but an optimal observer, Leuenberg optimal, because in deterministic sense control theory you know something is called Leuenberger observer. In the Leuenberger observer, you have a system has to be fully observable. So, you see A prime, say A dash C, A dash square C, that matrix, this will be observability matrix has to be full rank, okay, from deterministic point of view. Similarly, if you do live derivative and stochastic system observability, you will say Kalman filter observability is also proven. Now, EKF what it does, now why pseudo measurement is converging, now you can say now pseudo measurement converging, particle filter is converging, other higher method converging, but EKF is not converging, because EKF first of all you do not have, you have lack of system is little bit lesser observable than actual. Now, you are a total big nonlinear function, say tan inverse xp yp divided by x1 minus xp. So, this kind of nonlinear function you are linearizing using extended Kalman filter. So, it is doing the approximation around the mean only. So, it is an algebraic approximation, algebraic linearization around a single point and mean only. It is disregarding the probabilistic spread of your random variable, which is your x1. So, it is doing only one point. So, that is what the problem is all about with the first order approximation. If you use a second order EKF or a higher order EKF, maybe you will not see this. Well, it has not been done, but if you can, if someone is very interested or like this subject, can she run a Hessian implementation and see a second order EKF how it is behaving. Maybe it will work, maybe it will work. I am telling maybe because I have not tested it. You can, if you want to test it, you are welcome to do this. This is the problem with first order EKF. When the system lacks observability, then the problem with extended Kalman filter pops up. That is why in the bearing, when the people make the tracking algorithm comparison, they always take bearing angle only tracking problem. Bearing angle tracking problem is unique in its own sense, because you do not have any range measurement. You have only tan inverse y by x or theta measurement, and you are making it observable by putting some range constraint or by making some of the elements known, but you have lesser measurement. You do not have sufficient measurement to observe your system kind of thing. And now EKF kind of a first order approximation is kind of failing in those circumstances. But pseudo measurement filter, there is no approximation. I am operating on a simple pseudo measurement. Say I am just doing some algebraic manipulation of my using my line of sight angle measurement, and with that what I am doing, I am calculating the statistics and I am running a linear Kalman filter. So, there is no approximation as such. Well, variance calculation and all, they are partly accurate. Even you can test it with using some numerical value, you can test the expression of the variance also. So, these are, so that is the difference between an extended filter, extended Kalman filter and a pseudo linear filter. There is not much approximation involved. Only problem with the pseudo measurement filter is that it is, the covariance is conditioned on truth, and since truth we do not have, either you have to do with predicted estimate, there is no other way, or measurement also you can do it. But measurement anyway some bias may come and all, but that is why normally when we calculate the R matrix in measurement update cycle, we use predicted state, that is it. So, this is the thing. So, that is why your extended Kalman filter in such cases, but if you use now a radar tracking problem, the previous problem that I have shown, radar tracking problem, you have range, you have a angle, azimuth angle. So, system is very good observable, you do not need anything. Okay. Bearing angle only tracking problem will have, there are many type of bearing angle only tracking problem, not only this problem, there are other problems also. You see EKF is inferior, well they won't diverge, but it will be inferior, it will be definitely inferior compared to other things. Okay. So, with this actually I am about to complete two very important things, primarily pseudo measurement filter and extended Kalman filter. This will be heart of your target tracking, because next the intention of this course is to tell you the three functionalities. One is tracking, one is classification, sensor fusion. These are the total objective of the course. So, we have done some basics study, the estimation theory. So, brush up of estimation theory is done here, because this concept will be required for tracking, even for sensor fusion also. We will be using, when we do the tracking, the filtering we will use mostly pseudo measurement filter or extended Kalman filter. Okay. We won't use the further techniques which I shown a table sometimes back. If you remember this table, when I was studying the this course, and here actually I told what I will be teaching here. Okay, linear Kalman filter is anyway must. Okay, LKF, linear Kalman filter. Then we have already talked extended Kalman filter. We talked pseudo linear Kalman filter. So, these three things we have already discussed. And tracking mostly it is pseudo linear filter. It is very common and very efficient. It is kind of there everywhere, because mostly of the time you will do the radar or UIR measurements. So, pseudo linear filter, even EKF also to some extent, these are all good enough, or with the first order EKF, only Jacobian. These filters I will tell next, sigma point filter or something called statistical linearization, unscented Kalman filter. This I will talk next. Cubature we won't talk in this course, because it is not an estimation theory course. So, this filter or Gaussian Hermit or Gaussian sum filter, these filters we will not be able to talk. Even same is applicable for a sequential Monte Carlo filters, or called different kinds of particle filter as well. Particle filter also we will not be able to do it in this course, we will not have time. So, primarily in tracking we will be using those, even UKF also we will not use. There is another thing, why we won't use UKF or this method, because these methods takes time to execute. Okay. I will show you some example of UKF, how the UKF is built. If you understand the philosophy, the understanding of philosophy of UKF is very important. Once you understand the philosophy of the UKF, you will see why UKF won't be used too much in kind of our tracking application, because the processing time is a constraint compared to EKF or compared to PMF. Okay. So, that is why now I won't be kind of using UKF as a present. So, now again I would like to do some kind of brush up. So, what is EKF? EKF does algebraic linearization. So, you have a nonlinear function x dot equal to fx, y equal to hx, fx plus w, y equal to hx plus v. Okay. So, with this now when I run or execute an EKF, this nonlinear function fx, I make it f of x bar plus delta x. Hx also I do some linearization around a single point. Again I am repeating this word, single point. That point is your actually mean. So, here it is say your probability distribution of any random value. So, this concept will be required for the next lecture. So, that is why I am repeating it once. So, this is your mean value, okay. This is your variance value. So, entire distribution I am mapping only based on mean. I am not able to kind of going to the spread of my random variable, okay, because I am doing it only one point. F of x, I am how I am linearizing f of x bar plus delta x, okay. With this now I am calculating its mean value and all. So, if you say it is y, so this is y, okay. So, y bar plus delta y is equal to f of x bar plus delta x. Now, expectation of y actually will be actually y bar into expectation of f x bar plus expectation of delta f into delta x plus higher order terms, right. This is your first order EKF. Once you take this value will be 0. So, it will be f x bar. So, my probabilistic spread of x is lost. This is the problem of EKF. This is the very big problem of EKF. So, and that is why you have seen in the earlier problem EKF has diverged. It one run, in one Monte Carlo run I saw my error shooted up, it simply diverged. This is the problem, okay. When your system is unobservable or less observability, degree of observability is lower in your system, EKF might show a problem, EKF will show a problem. Even navigation example also, when you are doing this GPS IMU integration, you might see there is a lack of observability due to your IMU, some of these IMU measurements, and that time EKF creates a problem. That time we use something called linearized Kalman filter, which is another, which is not a pseudo measurement filter, but it is a linear Kalman filter. So, linear approximation is always kind of a better, okay. Now, in next class or next lecture, we will be touching something called statistical linearization. So, now we have done with algebraic linearization, because this is algebra. What is this called? This is your Taylor series, first order Taylor series expansion. Now, we will be doing it statistically. So, I have a mean, I have a variance. I want to reproduce the distribution. How I will reproduce the distribution? By some numerical points or something called sigma points, okay. That we will be talking in the next lecture when we discuss the philosophy of EKF. So, with this I am kind of closing this lecture session. So, thank you very much for your time, and in the next class we will be starting the unscented Kalman filter basics only, okay. Thank you.